Hello, my name is Kyeong Jin Kim. I am from Mitsubishi Electric Research Lab in USA. This is the presentation for ICC 2020. My title is a dCDD-based transmit diversity for NOMA system. I have several collaborators such as Hong Liu, Hong Jiang Lei, Jiguo Ding, Li Li, and Professor Poor. This is the content of my talk. I will first introduce motivation of this work. As a system model, I will summarize the original distributed cyclic delay diversity, say dCDD, for single carrier transmission. And then I will introduce how to extend the original dCDD into NOMA transmissions. After then, I will briefly explain performance analysis of NOMA transmissions with dCDD. After showing some motivation to meet high spectral efficiency, ultra reliability, and low latency required by several applications such as tactile internet, mobile edge computing, beyond 5G networks, and others, NOMA has emerged as a key technique to meet these requirements. The fundamental idea of NOMA is to apply superposition coding in the power domain, so multiple users are multiplexed on the same time frequency resource block with a different power level. Even for NOMA, to enhance system performance and provide new degrees of freedom, various diversity techniques have been proposed. Especially in this work, we propose NOMA transmissions with multiple transmitters deployed in a distributed manner over a coverage area. However, it is challenging to obtain CSIT channel state information at the transmitter site to develop a new transmit diversity scheme. So the objective of this paper is to develop a new transmit diversity scheme that does not require full CSIT. This is possible by employing the dCDD that was proposed by the author and then proposed pseudo NOMA transmission, which is different from conventional NOMA that use superposition coding. Let me summarize the original dCDD. Let's see this system setting. There is one CU that transmits one single stream S, and there are multiple transmitters that has single antennas, and there is one receiver which has also single antennas. And we assume that these distributed transmitters are synchronized by means of GPS signals or the precision time protocols, like, so that we assume that this is the time synchronized system. And for the specific channels from the CU to a particular transmitter, it is recognized by a channel vector with its corresponding the number of multipath components. Now, to achieve the dCDD, the receiver needed to feedback partial CSIT. The first parameter is NCP. This one is the cyclic-prefixt length determined by the maximum of the multipath component over all the channels that are connected to receiver. Now, based on the estimated channel at the receiver needed to form a list that specifies the channel strength from smallest to largest. Now, based on this index, the receiver needed to form a list that specifies its order like this, and then needed to feedback these two parameters to the CU. Then, based on this one, the CU can select only a limited number of transmitters for the dCDD operation. Now, based on this available partial CSIT, it has been verified that maximum achievable diversity gain is given by this equation. Here, M is the number of transmitter in the system, and N is the cyclic-prefixt length. And based on the block size for single carrier transmission, say B, the available number of transmitter for dCDD operation is given by these equations. However, one of the other weakness of the original dCDD is that dCDD support only one symbol stream. So we need to extend the original dCDD into the another structure that supports NOMA transmission. This one is the brief system model. Let's see. As in the previous slide, there is one CU and RRH, say remote radio head, and two users, UE1 and UE2. UE1 is recognized as the file user, and UE2 is recognized as the near user. They are determined by the distance from a set of RRH to itself. And in this work, we use near far user pairing. That is, the rate of user 1 should be greater than the rate of user 2. Since this one is a very tight constraint in this system, we are working in how to assign power to different groups, say group 1 and group 2. And then we also working how to assign how many RRH are assigned to group 1 and group 2. So this one is the open problem in this system setting. And also, because the structures is used also dCDD, user 1 and user 2 need to compute its corresponding cyclic-prefixt based on its connected channels, say NGCP and NFCP, and then they need to feedback those cyclic-prefixt lengths to the finalized NCP. That is the maximum of cyclic-prefixt received from those two users. And since in the structures we are more focused on the UE1 that has required a higher rate, we use RRH that results in the stronger channel strength at user 1. So the user 1 needed to generate index that specifying the channel strength from the weakest to strongest, and also needed to feedback this list to CU as well. Then the CU can divide a set of RRH into two groups. So group 1 that is targeting at transmitting S1, and another group that is targeting to transmit S2. Now we also use a specific decoding order. Say user 2 decodes S1 first and then S2. And then user 1 decode S1 with an assumption of perfect decoding of S2 by user 2 by means of SIC principle. Now based on these structures and applying the dCDD and removing the CP's related signal, we have received the signal at user 1 and user 2. If you look at these two signal equation, we can see that the form is very similar. Say alpha 1 and alpha 2 is related with the power allocation, and T1 and T2 is related with the distance from a particular RRH to user 1 or user 2. And G and F are the channel matrix, and the P is the permutation matrix that is related with the cyclic CDD delay assignment at each RRH. And this one is the receive, this one is the transmitted symbol block, and this one is the additive noise vector. But there is the one difference between these two received signal, because this group is more like a focus on this near-far user pairing. So the order statistics are involved in the representation of this received signal. And now I'll briefly explain about the performance analysis, especially for user 2. We are mainly focused on the receive SNR for decoding S2. It is given by this equation. For user 1, is corresponding receive SNR for decoding SNR. Decoding S1 is given by this equation. And now, based on this defined SNR, we need to compute its corresponding PDF for these SNRs. But it is easy to compute the PDF for this SNR. However, it is not easy to compute the PDF for this SNR, because if you look at this equation, these two quantities are related with order statistics, and this one is related with the ratio of these two quantity. It is not easy to compute the exact PDF for this SNR. However, if we use some spacing statistics and using some kind of concept of matrix permanence, we can eventually derive the corresponding expression for the PDF of this SNR. This derivation is provided in the paper. So if you can see the paper, you can easily understand the derivation. And now available this PDF, we can finally derive the achieved rate for user 1 and user 2. Simulation results. At the setting, we assume that the block size is 32 and NCP is 6. So that 5 RRH can be possible for the CDD operation. But in these specific scenarios, we assume that there are 4 RRH placed at these locations. Also, UE1 and UE2 are placed at this specific location. Now, for the specific scenarios, say 3 RRH are assigned for the first group out of 4 RRH, and this is one is the case where 2 RRH are assigned for group 1. And now for this two different case, this plot shows the rate of user 1 and user 2. And especially from this figure, we can say that as the ratio of power for group 1 increase, the rate of the first user is increasing, but it is upper bounded because, as I explained, the SNR of user 1 in decoding S1 is the ratio of these two quantity. So as SNR increase, there is the performance limit like this. But if you look at this equation, the SNR of the S2 is keep increasing as SNR increase. So we can see a different behavior between two users. And especially for this case, we can see a little different characteristic depending on the power allocation for power allocation to first group. Say if power allocation to first group is either 0.6 or 0.7, then there is no feasible reason that meets near-far user pairing, because this one is the rate of user 2, this one is the rate of user 1. So if you look at this curve, this curve is always greater than this one, so that there is no feasible reason. However, if we increase the power allocation to first group, say 0.8 or 0.9, then there is the feasible reason. Say, for example, in this case, if the alpha 1 is a 0.1, this one is the crossing point between those two users. Say, so that only up to 36 dB is possible to satisfy this near-far user pairing constraint. Here are conclusions. In this work, we have proposed a new transmit diversity scheme for two-user pseudo NOMA, and to support near-far user pairing, a new joint RRH assignments and power allocation mechanism for TCDD has been proposed without requiring full CSIT. And by collaborative simulation, it has been shown that a light power allocation and RRH assignments are key parameters due to a near-far user pairing constraint. However, in general, it is required to assign as many as RRH to transmit the signal targeting at the far user and allocate more power to this selected RRH. If you have a question, please contact me by this email address. Thank you.